now that we have looked at our mole to mole ratios, now we're going to get a little bit more challenging. And we're going to look at grams to moles, and grams to moles to grams, right? So we know that our coefficients help us to balance our chemical reaction, and they represent molecule to molecule or mole to mole relationships. But the actual amounts of substance that we use in the laboratory are weighed out in grams, right? So we need 3 conversions when we are doing chemical arithmetic, when we are looking at chemicals in the lab. So we can't just go put a mole on the balance. We actually put a certain amount of substance on a balance and we weigh out the amount in grams. So we really can't use that mole to mole ratio to help us do math in the lab. So there are 3 different ratios that we'll look at. So we're looking at, I'm just going to go over the ratios right now. So we're looking at molar mass, gives us a ratio of grams to moles. Our mole to mole in our chemical reaction gives us our moles to moles. And our last ratio is going to be molar mass again. So if I'm looking at a chemical reaction, right? In order to convert from the mass, so if I'm given a problem where I'm given the mass of substance A, right? I need to convert that mass to our middleman, the moles of substance A. Now that I have the moles of substance A, I need to now compare that number of moles of substance A to substance B, whether it's a reactant or a product. We need to know who's the next middleman. So from there, I'm going to use the mole to mole ratio from our balanced equation to get the second number of moles, right? Now, if I'm asked the number of grams of that substance, I now have to go from the moles of B to the grams of B. And once again, I would use my molar mass, right? So how would I go all the way from the gram of substance A to the grams of substance B? I would first use the molar mass of A because grams are going to cancel out. Then going from the moles of A to moles of B, my moles of A cancel out. And then if I need to get the mass of B, I've got to use my molar mass again, and moles of B cancel out. So let's see what I got on here. So for the first step, the grams of A are going to cancel out to give me moles of A. In our second step, the moles of A are going to cancel out to give me moles of B. And in our final step, the moles of B are going to cancel out to give me the grams of A. So if I need to go from the grams of substance A to the grams of substance B, I need all 3 of those conversions, right? So if I'm going from grams of A, I need to get to the moles of A. Where's my pen? I want a different color. Get a different color here. Let's go blue. So if I'm going from grams of A to moles of A, that's here. Once my grams of A cancel out, right? I'm left with the moles of A. Going from moles of A to moles of B, I'm gonna end up with that once my moles of A cancel out. And the last step, getting to the grams of B, which is whatever our last substance is, my moles of B cancel out and I'm left with the grams of B. So for every problem that you're going to see using chemical reactions, you're either going to be somewhere within this range, grams of A to moles of A to moles of B. That's one type of problem. Or the grams of A to the moles of A to the moles of B to the grams of B. So you're going to have at least 1, 2, 3 conversion factors that you're going to need to use in order to solve these problems. So here we have our whole, if you read through the textbook, the reading for 7B, you will see something like this, but I turned it around so that it's in the other way. So all of these conversions can be carried out using different conversions. So you cannot go straight from the mass of one substance to the mass of another substance. You actually have to use our middleman. Remember, middleman, the middleman is moles. So notice the middleman in here is always the moles. Whether I'm starting with the grams of a given amount, I've got to get to the number of grams of that given amount. I mean, the moles of that given amount before I can determine the number of moles of the needed amount. So we can say that A is given, B is needed, right? So let's do some practice. All right, suppose we wanted to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen in our following equation, right? So here's our plan. We're going from the grams of A to the moles of A to the moles of B to grams of B. How do you know that that's the plan that you need? Because you're given the grams of a substance and you're told that you need the grams of another substance, right? So we first write what we need and what we're given. We're given 32 grams of nitrogen, and now we need the grams of ammonia. So we start off with the grams of nitrogen. In order for me I have to convert that grams of nitrogen to the moles of nitrogen before I can compare that to the moles of ammonia. So what is my conversion factor? I'm going to use the molar mass set up in this direction where I would cancel out the grams. Next, I need to get from the moles of nitrogen to the moles of ammonia. And we see here we need a mole to mole factor. So what would be the mole to mole factor based on our equation? What is the mole to mole factor of ammonia to nitrogen? How will we write it? What goes on top? We would write 2 moles of ammonia for every 1 mole of nitrogen. And then last, we are asked the grams of ammonia. So what is the ratio that we're going to use? We're going to use now the molar mass of nitrogen. I mean, not of nitrogen, of ammonia. So now that we have our plan, we're going from grams of nitrogen to grams of ammonia. We're going to use these 3 conversion factors to solve our problem. So we need grams of ammonia. We always start with what we're given, 32 grams of nitrogen times our molar mass of nitrogen, which is moles per gram, 28.02 grams, times our next conversion, which is going to be 2 moles of ammonia for 1 mole of nitrogen. And then our last conversion is going to be our molar mass of ammonia, which is 17 grams on top, 1 mole on the bottom. To check yourself, always make sure that your things cancel out properly. Our grams of nitrogen cancel out with grams of nitrogen. I'm left with moles of nitrogen. Now our moles of nitrogen cancel out, and I'm left with moles of ammonia. Our moles of ammonia cancel out, and I'm left now with grams of ammonia So when we put all of that in our calculator, we get 38.92 grams. Sha, is my math correct? That's my math corrector. So how do I put that in my calculator? I would say 32 times 2 times 17.04 divided by 28.02, right? So we have two significant figures. So our answer should be what? $39.
0.0.
No, if I put 0.0, that gives me how many sig figs?
So then it's going to be 39 with a decimal point.
We don't need the decimal point because 9 is a number. 0, if there was a 0 at the end, we would need the decimal point. So, but because there's no 0, we just write 39. The only time we would write a decimal point is if this digit here, the 9, was a 0. Then we write the decimal point to say that that 0 is significant. All right, so there are quite a few problems on here. What time do we have? It's 10:43. We're gonna work some of these out together. So make sure you have this slide pulled up, and I'm gonna go on to another slide to do all the math, okay? So number one, so we have our equation written here. Our first question was asking for, our given amount was 5 grams of oxygen, and we need moles of iron 3 oxide, right? So what's our plan? We're going from the grams of oxygen to the moles of oxygen to the moles of iron 3 oxide, right? So being that I have 2 arrows there, each arrow is going to represent a conversion factor. So what would be our first conversion factor? Anybody know? You will always know what's A because A is given, B is needed. A is what you're given, B is what you needed. So the first one we need is grams to moles, which is going to be our molar mass. And number 2, we're going to need what? What's our second conversion that we're going to need to get from the moles of oxygen to the moles of iron 3 oxide? Right, we need a mole to mole ratio from our chemical reaction. So we start off with what we're given, 5 grams of oxygen times our first conversion, which is going to be the molar mass of oxygen, 1 mole per 32 grams of oxygen. Next, we're going to use our second conversion, which comes from our balanced equation. What is the molar ratio of our balanced equation? What goes on top? Let's see, Armando says 3, well, how many moles is it? How many moles? Yes, 2 to 3. So I've got 2 moles of iron 3 oxide for 3 moles of oxygen. Our grams of oxygen cancel, our moles of oxygen cancel, and we're left with moles of iron 3 oxide. So we know that we set up our problem correctly. How do we put this in our calculator? 5 times 2 divided by 32 divided by 3. We get this 0.104. How many significant figures must we have? 2. So what's our answer? If we need 2 sig figs, what's our answer? Does everybody agree with Matthew? Oh, Sha, where you get 0.31? .10 or 1.0 times e to the minus 1. Correct. What, Sha? You can't get things wrong. You can't get things wrong. You're supposed to be helping me out. No. All right. Number 2. Number 2, our given amount is going to be 45.8 grams of iron 3 oxide. I know Superman has weakness. Oh, she's my Superman. And our needed amount is the grams of oxygen. All right, so what's our plan? I want somebody to write the plan in the chat. What's the plan? We got grams. Somebody crying in the background? Make sure you mute yourself, folks. What's the plan? What's the plan? What's the plan? What are we doing here? I want the whole entire plan. I'm going from grams to grams. Yes, Sharona, but how do we get there? We got to go from grams to what? To moles, then grams to moles to moles to grams. Right, this is a grams to moles to moles to grams. So grams to moles to moles to grams. And we need our molar mass. So if we got to go from grams to moles of a substance, we have to have the molar mass, right? So let's set this up. The number of grams of oxygen is going to be equal to what we started with, 45.8 grams of Fe2O3 times our molar mass. What goes on top? The moles or the mass? Moles goes on top. Thank you, Adam. And grams goes on the bottom. Our next conversion, what do we need? Oh, I gave it to you already. We need our 3 moles of oxygen to how many moles of Fe2O3? 2. And then our last ratio is going to be what? Where'd you guys get 1? Our molar ratio is 3 to 2. So I need 3 moles of oxygen on top of 2 moles. And yes, 32 grams of oxygen per 1 mole of oxygen. How do we put this in our calculator? 45.8 times 3 times 32 divided by 159.7 divided by 2. Our grams cancel out. Our moles cancel out for iron 3 oxide. Our moles of oxygen cancel out. And we're left with grams of oxygen. So as long as you set up before you even do your calculations, make sure that the things cancel out properly. Grams of, and then you do your calculation, okay? And if you do it that way, you're most likely to get the answer correct. If you don't get the answer correct, then it's maybe because you either put the wrong values or you plug things into your calculator incorrectly. And being that we have 3 sig figs, our answer must have 3 sig figs, so we get 13.8. All right, here we go. We need to know the grams of oxygen. We're given 25 grams of potassium. So we're going from grams of potassium to moles of potassium to moles of oxygen to the grams of oxygen. So we start with our 25 grams times 1 mole over 39 grams of potassium. Then we have 1 mole of oxygen per 4 moles of potassium. And then our last one is 32 grams of oxygen per 1 mole of oxygen. Our grams cancel out, moles of potassium cancel out, our moles of oxygen cancel out, and the answer is 5.115. We need 3 sig figs, so our answer is D. Remember I said at the beginning that sometimes you can start off with a certain amount of product of reactant, but you really don't always end up with the total amount that you've calculated, right? So the actual amount that you get in the laboratory is called actual yield. The theoretical yield is the amount that you've calculated. So we've been doing theoretical yield all this time. Theoretically, if I start with this amount, how much do I get? Theoretically, If I start with this amount of reactant, how much product do I get? That's theoretical yield. Actual yield is the product that is actually obtained during our experiment. Does this percent yield, does this thing look familiar? It should look familiar. It should look like our percent concentrations that we've had before, right? So the percent yield is going to be our actual that we get in the lab versus what we thought we would get times 100. And remember, we can always rearrange this equation to solve for whatever we need, right? So if we're given the percent and we're given the theoretical, we can rearrange it to get the actual. Theoretical, you will almost always have to calculate, okay? So let's do some practice. When 26 grams of acetylene is burned in sufficient oxygen for a complete reaction, the theoretical yield is 88.0 grams of CO2. Calculate the percent yield if this reaction actual yield is only 72.4%. Well, we have our percent yield is actual divided by theoretical times 100. So we're given the theoretical and we're given the actual. So our percent yield is just going to be our actual divided by theoretical times 100, and we're going to get 82.3%. That one was a simple question. Why? Because we were given both the theoretical and the actual. But you know, we can't be that simple, guys. Absolutely not. So let's try a trickier one after this. All right. The reaction of ethylene with water to give ethyl alcohol occurs in a 78.5% yield. How many grams of ethyl alcohol are formed by the reaction of 25 grams of ethylene? What are we given here? We're given the percent yield and we're given a starting amount. So what do we have to calculate?
The theoretical yield.
We have to calculate the theoretical yield. I'm breaking up, my bad. Sorry. Is there ever questions we would have to answer if they weren't presented in class? So I only did that one time because we went over all of them. All right, we got 1 minute, guys. So we have to calculate the theoretical yield in order to get our actual yield, because really this question is asking for not the theoretical, but the actual, right? But given our equation, remember we have percent is equal to actual over theoretical. So what do we already have? So if I rearrange everything around for the actual yield, what do I already have? I already have the percent. And I need my actual, right? So before I can calculate the actual, I have to calculate the theoretical. We've been doing theoretical all this time. So it's grams to moles to moles to grams. So we're given our percent, we're given our starting amount. So before we can calculate the actual, we have to calculate the theoretical. So we have to calculate theoretical first. So starting with what we were given, 25 grams of ethylene. We got 1 moles of ethylene, 28.06 grams of ethylene. Based on our reaction, it's 1 mole of ethyl alcohol for 1 mole of ethylene, and 46 grams of ethanol per 1 mole of ethanol. We end up with 41.1 grams. Now we can calculate our actual yield. So that's our theoretical, and actual is going to be theoretical times the percentage. Our percent yield is 0.785 because that's the percent divided by 100. and we end up with 32.3 grams of ethyl alcohol.